So just the epsilon, right? EMF, epsilon.
Yeah.
Motive force, yeah. Any question about this idea?
Could we like go over it?
Yes, it's presumably you are studying the DC circuit, right? At the moment. Power supply.
I don't know. I don't think so.
So the context of this idea was proposed when we described the battery. So if you have a battery, so EMF is associated with the battery, see? So when we describe the battery, and this number one is positive side, so this is a battery. So if you use a voltage, if you use a voltage to measure this volt, then you can read the voltage drop across a battery, right? So we normally say the battery whose voltage is, say, for example, 12 volt, right? However, traditionally we don't use a V, we use epsilon. That is the context of this. This is epsilon. We use EMF. Actually, it's not very important idea. It's just it's not the force in the first place. So it's called electrical motive force. Motive force. So it's not the force. Okay, it is a potential difference of voltage. So what we call this a voltage. Are you talking about this idea?
Mm-hmm.
So this first case is real battery. So this ideal battery. So this is first scenario is ideal, simplified ideal battery. However, in the real battery, so for this ideal, go to the real battery, then we have to consider internal resistance. Did your teacher mention this idea? For the real battery, apart from this simple, which just means there is a potential difference, then we have to consider there is a tiny equivalent. There's no such resistance, but just equivalent. So as a whole, these two components is considered as a real resistor, real battery, Did your teacher notice that?
No.
So the R, so yeah, R is called the internal resistance. Internal resistance. As if there is a resistor inside.
Mm-hmm.
So this time, if we use this traditional notation, so this would be the epsilon. Can you see? Motive force. And because in those days, there's not, if they cannot describe anything magic, they just use force. Okay, they describe the battery as if there's a force which can move the electron. That's why they have this electrical motive force. But it's not a very good idea. But in this case, if you want to measure the voltage drop, we still can use the voltage meter, right? Now, in this case, you have to be careful. So the voltage meters, the voltage you measured is not equal to epsilon anymore. Can you see? Do you know why?
No.
Because there's a resistance. Can you see?
Yeah.
So if if you assume there's a current, if this is a current, so if there's a current that goes that direction, the current, electric current. If there's electric current, then you have to, then in this particular case, the voltage you measured will equal to epsilon plus the I multiplies R. So in ideal battery, we assume that the internal resistance is 0. Is that what you? Is relevant to your question? Are these
really?
Yes. So that is why we have to be careful when we when we're dealing with Ohm's law, we have to ask whether whether this battery is ideal or real, right?
Mm-hmm.
They will tell you. Don't worry. They will tell you. For example, when we have a problem, they will tell you. So the battery, and they will mention that if there's a battery, have the internal resistance. If they do, then you just draw another resistor here, realizing this is just part of the real battery. You see. So I still use a small r for internal, and external r for r. Otherwise, the law, we still can apply the Ohm's law. See, is that your concern? So in this case, if you apply Ohm's law here, and the voltage across the battery, so this is V, can you see? So then you have to consider the so basically, do you still remember Kirchhoff's law?
Yes.
Yeah, so Kirchhoff. So he had two laws. One is a voltage law. So one is about voltage. If you use a voltage law here, voltage law. So then what we can do, we can just follow this notation. So I multiply R and take plus I multiply internal resistance should equal to the voltage, the electrical power force. Can you see?
Mm-hmm.
So that is a Kirchhoff's law about the voltage.
Yeah.
So don't worry. So epsilon EMF is that is one context where you can use this idea. Another context is when we're talking about the Faraday. You know the Faraday, microfaraday law. That's in the probably also you also encounter this idea in the Faraday's law. Faraday's induction law, electromagnetical induction. Do you know the induction? Not yet.
No, not yet.
So basically, what happens if you got to the solenoid, if you have the, for example, if you use the coil here, so if you use the coil, what can I say? How can I draw that? So if I use a coil, let's use a circle, let's draw the circle. This is part of electromagnetic phenomena. I don't know if you have studied this part or not. So if this is a coil, and then we change the magnetic field inside. For example, this is a magnetic field, right?
Mm-hmm.
The magnetic field inside can be changed. The direction, not the direction, but the strength can be changed, right? So the B became time dependent. It's not a static force. What we can do here is we can just we can connect this terminal with this one, right? And then connect them with the battery, so the resistor. And then you can use the ammeter if you wish. And also we can measure. We can also measure. It's a bit crowded here. So we draw that. So basically, if you connect this coil here with the resistors, so this is the resistors. So to that. So you can actually see something very surprising. No battery, can you see? This time we use no battery, just the coil. And then you can measure, as I said, you can measure the current with ammeter. In the meantime, you can also measure the voltage as if this is connected with the battery. So what would happen if you change this magnetic field? You will see depending on which depending whether the magnetic fields increase or decrease, you will pick up the current like this. You see This current like this, that direction. So eventually you will measure the certain voltage drop across this loop. So this phenomena is called the magnetic induction. In other words, the changing magnetic field can generate electricity. Have you heard of that?
Yeah.
You do,
Yeah.
you do, yeah.
Mm-hmm.
Probably in this context, the Faraday law can be written as epsilon or equal to. Have you seen this notation? This is phi dt.
No.
No? Oh, that is a Faraday's law.
Mm-hmm.
And again, in this context, this is also called EMF. This EMF is not generated by battery, but by the changing magnetic field. So what is the phi here? Phi is called it can be defined as the product. Or you start vector, right?
Mm-hmm.
The vector is as two vector, the B delta product, the A for area, you see. In this case, because in this case, the directional vector, we discussed the direction of plane. In this case, how do we describe the direction of this circle? You can use a vector which is out of page. Do you agree?
Mm-hmm.
Out of page. So in general, you can see that if you use the vector dot product, you can write this as B multiplied area multiplied cosine theta. So this is just our dot product. Can you see?
Mm-hmm.
So in which this phi is called the flux. It's called the magnetic flux. Magnetic flux. And this is magnetic field. Magnetic field. And what is A? A is the area, the cross section, the area of the cross section. Of the coil. In this case, area is just the area of a circle. Do you agree? It's r squared, pi r squared, if that radius is r.
Mm-hmm.
So this is the simplest electricity generator.
Yeah.
Okay. Yes, I can show you something here. This is can I show you this this experiment, actually how the actual experiment is done? I hope the connection is fine. Magnet. That's really good. So doesn't work. I'm going to use this for a while. I'll demonstrate. Sorry, this is out of order. Anyway, it's just if you can, that's how the electricity generator work. You don't have use battery. So in the power plant, they don't have battery. But what they have is a rotating. They have a rotating magnetic field. So that when they rotating the field change, they can make the electron move. Hence, you will get the equivalent electricity source other than battery. So this is how to generate electricity. Well, you have to tell me where are you starting now, because they are totally different areas. So this is dealing with DC battery, DC circuit, and this is talking about how to generate electricity by change.
I think we're doing this one now.
Yes, it's called electrical induction, right? Electromagnetic induction. Yes. So yeah.
We also studied something called Lorentz law.
Yeah, Lorentz force, right?
Lorentz law, yeah.
Lorentz law is a force. It's a Lorentz force, yes. So you have the Lorentz. So Lorentz found the formula for the force. The force, let's have the force actually. This law is governing. Oh, no, don't confuse with another one. It's called another called the Lenz's law. That's called Lenz's law.
I think this is Lorentz one.
Lorentz law, which one? So they have Lenz's law. Lenz's law.
Something about particles.
Yeah, the force on the particle. Yes, that is a force. That is Lorentz force. That is a force. The magnetic force on a moving charged particle, a moving charge, right? So you have charge flying in space. If you have if the direction of velocity is known, say this is velocity direction. Did we talk about this before? Did we talk a Lorentz formula before?
No, I don't think so.
Not yet. If this time I just make the magnetic field is into the page. So there's a magnetic field into the page. Can you work out the force? Direction of the force. So this is charge Q. Charge Q. So these are two different laws. Lenz's law is different. Lenz's law is about the electrical induced electrical voltage. Do you remember this formula? The force F is equal to Q vector. Vector, that is the cross product of these two vectors. So you are studying vectors, so that will be very useful. The Lorentz force, if we put air here, can be written as the cross product of velocity and the magnetic field multiply the charge. Yeah. According to this, according to your knowledge of the cross product of two vectors, can you work out the direction of the force?
Isn't it just going? Isn't it just going that way?
So this is magnetic field into the page. Can you use arrow in this graph to indicate the force direction? Can you use arrow to indicate the force direction?
The force going this way.
It means double check. So if I use right hand, no, it's other way around. How did you get it downward? Did you use the right hand or left hand?
Oh, left hand.
Yes, left hand is very confusing. This guy is called flaming. Many textbooks don't use this law anymore, right? So I think if you combine this idea with the mathematics, then you will easily to solve this puzzle. So in this case, the force is down upward. This will be the force of Lorentz force. Why? Because according to mathematics, can you see? If you can make, this is 2D diagram, by the way, this is a 2D diagram. That's why we have mentioned whether it's into the page or out of page. So when you study this part, or when you study the vector in mathematics, you have to be careful with the diagram, the 2D diagram. If I draw the 3D diagram, as we did, when we studied the space, 3D space, then we can draw, I can put this 3 direction face green color to represent the velocity. So this is velocity. Make us change the side. Okay. So this is velocity, right? And the direction of the magnetic field, if I use a blue color, or because that direction, not necessarily, it could be perpendicular, doesn't matter, all right? But in the same plane, can you see? Oh, this is 2 vectors in the same plane, right? So this is magnetic field, and this is velocity, which are the same plane. Oh, by the way, the question we discussed on Wednesday is actually simple. If you want to know if you want to use 2 vectors to determine the plane, then you just need to work out this cross product, because this cross product will give you the direction, will give you the directional vector. You see? So that the cross product will determine this n vector. So once you know the n vector, which is contain the 3 components, right? A, B, C, then you should be able to work out that particular plane. So in our case, the product is not called n, but this time the third vector is called the force, Lorentz force. Can you see?
Yeah.
But this still satisfies this cross product principle. Do you agree? So in other words, in this case, this force is perpendicular to both. Can you see?
Yeah.
To both B and A. So you can imagine that you have the plane. You see that is you can use your knowledge of mathematics to understand this chapter. So you can imagine you have the plane. Can you see? So these 2 vectors were in the same plane. Can you see? These 2 vectors will determine the plane, and whose normal direction is actually the direction of the force. So yeah.
What does that mean? Like,
well, so the Lorentz formula is actually involves 3 vectors. Can you see? 3 vectors. 2 are in the same plane. So V and B are in the same plane. You see? V and B are in the same plane. Do you agree? In this diagram?
Yeah.
In the same plane. But the force is perpendicular to this plane. So this, if you do want to draw the normal direction, that would be normal direction. Can you see? That would be the direction of the plane. Can you see that? The same. This is normal direction. Can you see? Which is perpendicular to this plane. Can you see that? It's just the plane. This is the vector, which is perpendicular to the plane. Can you see? Now, how do we use this? Show you how to use the right hand rule to determine the force. You use 4 fingers, right hand, not left hand. 4 fingers toward the first vector, which is velocity. All right.
Yeah.
And trying to naturally burn your 4 fingers towards the direction of the second vector, which is the magnetic field. All right. If you can do that, then the sum will be direction of force. Otherwise, if you cannot do that, you have to twist. Okay, you have to twist.
Yeah.
So that is easy way to determine the direction of the force. So I prefer this right-hand rule because you don't have invented a new notation. And besides, this is also the similar to the relation between the two vectors, these three vectors. So for example, when we study the three space, we got X, we got Y axis, we got the Z axis. So we're going to use this 3D coordinate all the time when you study the planes, right? When you study a straight line and a plane in a 3D. So this is Z, this is Y, this X axis, right? And we have the three directional vector whose length is unit. So we have I, do you remember this I? Maybe use, do you remember this is I? And let's do some different colors. So this is I, change the color. This is a J, oops. This is J. And another one is Z, you see? You can use different color. Just remind you, the relation between these three vectors are similar to the relation in these three vectors. In mathematics, this vector is called I. The green one is called I. The direction of Y is called J. And the direction of Z is called K, right? So tell me, so what is I cross product J? Use your right hand rule. So you use your forefinger, go to I direction and burn to toward the Y direction. If that is the case, then the sum will be the direction of the K.
Yeah.
Okay, can you write the result here? What will be the result? Good. Okay. One more exercise. How about I cross product K? What is the direction of this cross product? I, K. You have used right hand, go to I, right? Go to I direction, and then trying to burn it forefinger naturally toward the direction of the K. The sum will give you direction. Yes, negative J, yes. Can you write down? Negative J, yes. Yeah, similarly, we can do some exercise in math for example, this time if the magnetic field is auto page, can you see? Well, here is a 2D diagram. So we will keep this. This is 2D diagram. If that represents the uniform magnetic field, can we call this as B? Now, if the negative charge, this time is a negative charge. If negative the charge is moving towards downward, so the velocity is downward. What would be the direction of the force in this case on this moving charge? So this is velocity.
Would that be force?
This is double check. So if you go to the direction of the velocity, right? But because it's negative, you have to go to upward. Can you see? Because for the negative, you have to reverse the velocity.
Or is that negative velocity?
Or you can alternatively you can find the direction of the force for the positive charge and finally reverse that direction. We will see. Okay, we'll check if this is correct. So the direction of the moving particle is downward. downward, okay?
Mhm.
Downward. So when we burn, yeah, that's when we burn forefinger toward direction of the velocity field, which is downward. The sun will give the direction of that force. But that is for the positive charge. Can you see?
Yeah.
If I extend that one, so you have, this is something we need to be careful. So if I just extend this uniform electrical field, we just compare with positive charge to see what was, well, the result you work out, this is positive charge. If the positive charge go downward, right? And then you'll be right, you were right. If the velocity is downward, maybe just different color. Yeah. So if this is velocity of particle for the positive charge, then you are right. In this case, the force will be toward the left-hand side. Can you see that? So the can you see the forefinger toward the velocity, and burn the forefinger toward the direction of the field. The sum will give you direction of the force. So this is a direction of the force acting on a positive charge, right? However, we know that when you multiply negative vector, the charge, the force will change direction. Can you see? Because you have considered this Q here. In this case, Q is positive, but in this case, Q is negative, right? So when we trying to work out the force direction on the negative charge, we can use the right-hand rule, but at the end we have reversed the direction. Or you have to multiply -1. Can you follow me? So what is the correct direction of this negative charge? So in this case, charge is negative. That's right. Does that make sense now?
Yeah.
So you can in practice, you can always refer to this 3D, use this 2D diagram, right? But you can also use the 3D diagram, because that would be more general, you see. But it's difficult to draw. You see, this side is a 3D diagram, you see. Does it make sense? Yeah, we can. Yeah. Do you have any question, or shall we change the subject? Or do you have other question to be discussed?
No, can we, I know we're doing magnetic flux next. Can we do that?
Yeah, so you want to study this flux, right? Magnetic flux. Yes, we can do some exercise. We can to see if you understand is flux, okay? And importantly, what is this angle? You have to pay attention to this angle. Can you see? How can we work out this angle? So this angle, by definition, is the angle between these two vectors. Okay. So one is a magnetic field. Another is area, direction of the area. Okay. Can we say, we can use this color, so direction of the area. Of course, this angle could be different, right? So by definition, this angle is from the theta, from the B to A, see? So that would be the angle, so that would be the theta. So that is something you need to know. So a flux is just a dot product. So which would be the scalar, right? Which would be scalar. So that you can write this as A multiplies the normal direction, the directional. In this case, be careful when you use the n, and in many cases, this is a unit vector. You see, if A is not a unit vector, you have normalized to unit, right? for example, you know the if you know the n is a parallel to the vector the vector a, right?
Mhm.
But the a is not a unity vector, so how can we write the n? So you have to use a. You have used a divided by its magnitude in order to get a unity vector. Can you see that?
Mhm.
So if you want to write it, you sometimes we just use we just consider a as a vector. That's all. Okay, let's do some problem solving.
What is like magnetic flux supposed to be measuring?
It's just mathematical product. It's just mathematics. You can imagine. You can imagine that there are many. There are certain. You know the electrical field. For example, if you have the you can we just draw a 3D diagram. For example, this is a 3D the circle, right? If this is it's just the circle. It could you can just consider this is just circle in space, all right? However, if you can work out if on the other hand, if you also can if you also given the direction of the magnetic field, right? If you know the direction magnetic field goes through this circle, some of you see, so this magnetic field, you see. So that allows you to work out their product, the dot product. Of course, probably some magnetic field is outside, but you don't have to consider the magnetic field outside. You only consider magnetic field line through this circle, through this area. So that's represent the magnetic field B. So this is what, do you remember? This is what we called that? They call the magnetic field line or force line. We call the magnetic force line. So this blue line represents the magnetic field at different position in space. So if you consider that if you want to work out the flux is just a dot product, you see? So you can consider this. Can you imagine this area inside the circle? Can you imagine that?
Yeah.
And in this case, the directional vector of the circle is not in the same direction. Can you see? So you can use this one. So that would be the direction of the circle. Can you see? Yeah, that in this way we actually use your knowledge in mathematics. Can you see? That will represent the directional unit vector of this area. So this is area. Can you see? Of course, in this case, area, in this particular case, the area is equal to the pi r squared, right? It could be a circle, could be any shape, but there's area circled inside a circle, a loop. Can you see? Yeah. So this is just a loop, This loop could be the metal, it could be a coil, or could be just the imagined area, okay? So what is a flux? Flux, in this case, you have to work out this product. And actually, it should be the integration. Have you studied integration? Yes? Yeah. So basically, this is a simplified form in which we assume the magnetic field is a uniform. Okay. In this case, what we have to do, we have to work out the direction of the magnetic field. Can you see this is theta? Do you agree? So once you know this theta, in this case, then the phi, the flux, we call the flux. You can imagine this flux is kind of, this blue line represents some kind of flow, okay, like water, yeah, or gas. Yeah. But of course, there's no such visible flow. It's just the mathematical flow. It's called the flux. So mathematics can describe this distribution by analogy of with the real flow in space. So by definition, according to our formula, and this flux will simply equal to B dot product A. And in this case, we know that the angle between this direction of the area and B is the theta. So therefore, it's just equal to BA cosine theta. So that is how to calculate the magnetic flux.
Yeah. So is flux the movement of it?
No, the flux is a product of magnetic field and is the area determined by this loop. That makes sense? Closed loop. This loop is closed. It's just allowed to draw. So a loop can we just draw the general scenario? A loop could be the square. Can you see that? And could be the circle, or could be ellipse, or could be irregular. Can you see?
Yeah.
They're all loops. So what do we care? What do we care is we just need to work out this. If it just is uniform, so we are interested to work out this area determined by the loop, and using this area and its direction. Can you see? And its direction to multiply the magnetic field through this area.
Yeah.
Okay. Now this is if you have studied mathematics, we probably can consider a general term that will help you to understand what is a flux. A flux could be like this. Can we just consider 3D scenario? This is a how to say it? This is a sphere. Can we consider the sphere? Yeah, I think you were eventually you were not. I think in you don't know how you don't. I just drew this 3D diagram for you. So this is 3D. So basically, so in this 3D diagram, if you want to work out, you just how to draw this properly. Can we just consider a quarter of that? So we just consider this. Just look at 3D. Can you see? If I just work out a quarter of this, so this is a. Can you imagine this like a sphere, like Earth, right? So this is a 3D sphere. Now, if you imagine, if there's the source, so this is a source of the this is one pole of the magnetic field. Can we just put a magnet here? So we will put a magnet here. If we put the magnet here, so for example, we put the north and the south. We put the magnet at the center. So this is north. Is north and south. Can you see? So you can, in this way, we can work out the direction of the magnetic field. Can you see? Can you see that? So that is a magnetic field. So that's similar to the Earth. Do you remember the Earth is a huge magnet? Okay. So in this case, I just draw one more, I think. I just make it symmetric. So this blue will represent the magnetic field. You see? That represents the magnetic field B. So that's the magnetic field B. Now, this time you have to be careful. If you choose the area, if you choose an area in the surface, can you see this is area, and at a different position, the flux will be different. Do you know why? Probably at the center, if you put this one here. For the same area at the center, you will get the magnetic field almost perpendicular to the surface. Can you see that? However, if you pick up the side area, you will notice that the magnetic field is always almost parallel. Can you see that? In this case, in this case, theta is very close to 0. While in this case, theta is close to 90 degrees.
Yeah.
Does that make sense? So if same area, but if the angle is different, their flux will be different. So therefore, in this case, the flux, magnetic flux were very close to 0. And were in this case, what would happen for the magnetic field in this case? That is a B dot product A, right? Were equal to BA multiply the cosine theta, right? Because theta is very close to 90 degrees, so therefore it will very close to this B multiply A. Can you see this is A? The blue one, the green one is area. Can you see? So this diagram show you that the for the same area, the flux can be different.
Yeah.
That makes sense. Perhaps we can take another example. If you have, for example, if you have we still continue to draw this 3D diagram. So this is a loop, right? A rectangle, and also this is also the loop. You see. In the first case, can just focus on first case first. If the magnetic field is go that direction, right? Okay. So this is uniform. In this case, the magnetic field is uniform. So therefore, we can easily work out the angle. This is angle between its direction, normal direction. Can you see? That's direction of area. So in this case, the flux in this case is simply equal to this called area. Or if you know that if this is A and B rectangle, the flux is just equal to B multiply AB. Can you follow me? And multiply cosine theta, right?
Yeah.
On the other hand, if you consider this time, we just rotate this loop. This loop is just hypothetical loop, or could be the loop of a coil, right? Now, if I just rotate that, so this just consider another direction, another scenario. In this case, if the magnetic field is perpendicular to the direction of the normal direction, can you see that? So that is magnetic field in space. In other words, in this case, the direction of this area is actually perpendicular to the magnetic field, isn't it? Okay, in this case, what is the flux? So what is the flux?
Since it's perpendicular, it would be 0.
Yes, it's always 0. Yes, in this case. Okay, let's go to something real. That is an electrical generator, right? So if you have if I draw this diagram for you, this is a 3D diagram, because the 3D diagram can be easily understood. But you have to get used to that. Sometimes we use a 3D diagram, sometimes we use a 2D diagram. So this is just part of magnet. And on the other side, we got this curved. The reason we use this shape is in order to make the magnetic field is uniform between the gap, you see? So that would be the south. And in the center, we have built the coil, we have built axis, rotating axis. So in the center, we can actually build the axis we can rotate. Now, what would happen is if you build this time, if you build the coil here, if you coil here, Can you imagine there's a coil? Like we can use the copper wire to make the coil conductor. You see?
Mm-hmm.
Of course, you can also consider this is just a loop, right? Can you work out the direction of magnetic field and the flux in this case? So here probably I have to draw another. So basically here in the center, this is just a loop. So this can rotate it, you see.
Mm-hmm.
And how can we determine the angle? Can we just make the angle? So this is angle. Can you call this alpha? This is angle. So the angle can be changed, but at this particular alpha angle, can you work out the flux in this case? Yeah.
Would this be the magnetic field?
Yes, from north to south. Yeah.
Mm-hmm.
Yep.
And then
so what is direction of this? Can you use the arrow, read color to determine the direction of this loop, rectangle loop?
That way?
No,
Like the
nearly,
force would go that way.
nearly not perpendicular. You have this is 3D diagram.
Mm-hmm.
Can we draw them more? Can we draw one for you? Should be go that direction. Can you see?
Yeah.
We should be perpendicular to this yellow, another yellow origin color. Can you see?
Mm-hmm.
Can you imagine that?
Yeah.
So in this case, if you can draw one more magnetic force line, can you see that there is angle now? Can you see?
Yeah.
So this angle is determined. This is angle determined in the formula. So this will be the angle. Okay. So this angle and this alpha is the same, isn't it? You see?
Mm-hmm.
So you can see. So if this rectangle, if this side is A, other side is a B. Can you write and we denote this magnetic field as a B? Can you find the magnetic flux in this case? So this is also the alpha.
On color.
Good. So this time the phi became the function of alpha. Do you agree? If the field is fixed, so that became the function of alpha. That's very interesting. Okay. Can we just can we work out the diagram? So the another thing we will need to know is work out the diagram. If I use this vertical is a flux, okay, and this will be horizontal will be alpha. Can you draw the graph for the flux in this case? So this is the flux, and this is alpha. Or you can use theta. Up to you. Maybe we consistently use the theta. All right. Otherwise, can we just yeah, it is a cosine, right? It's cosine function. So basically, we have this. So I change it to theta. Otherwise, get confused. We don't have introduce. We can just introduce this alpha. This theta as well. So let's just rewrite this part. This is our theta. So this is also the theta. This is theta. Okay. So can you label this part? So this is 0, right?
Mm-hmm.
Yeah. half pi, right? That's theta pi, right? What is the maximum? What is the minimum? What is the maximum? What is the minimum? No, AB. Can you see? This is a magnitude. Can you see? Should be negative BAB, right?
Oh, yeah.
And magnitude, yeah. You are fine. This is the first time you encounter this abstract idea called the flux. Doesn't matter. It's just we know which can be we can define this flux if we know the magnetic field and the angle and the area, right? So
yeah.
So you can see that sometimes the flux is positive, right? And sometimes negative. And more importantly, you know that in this case, oh, by the way, how can we draw another one? Can we just also draw a diagram for d phi dt? First derivative. Can we draw the first derivative? Mathematically, how can we work out the d phi dt? So this is a phi. Can we use a theta?
It's negative.
Negative, yeah.
D sine.
Okay. Okay. Now, how this is design? How about the negative? Because what we in the Faraday law, we need to know the negative d phi d theta, dt, d theta. Sorry, d theta.
Sine theta.
Yeah, become positive, right? Yeah. Okay. Can you draw this one, which is just sine, right? Sine. Can you draw that? Can you use a different color to draw this on the same diagram? Yeah, but probably this is just a sketch, all right? It's not accurate. Maybe we need to find some space to draw it accurately because that will doesn't matter. I can find the space somewhere. This time we be careful. We just make sure we understand they have the scale must be correct, all right? Because that's that will determine the outcome of your because every curve will represent the physical quantity. Now this time, can we just divide that into 4 equal terms? So that's 1, 2, 3, 4. All right. That would be more accurate. This is theta, so that would be half pi. It would be the pi, right? That is 3 pi over 2. That would be 2 pi, 1 period. Okay, that is can we draw this on this side? Can we draw the can we draw phi first? Can we just draw phi again? Can we draw flux again? So this is maximum, this is minimum. Can we draw this blue one again?
Yeah.
That would be maximum. That would be the minimum, right? Yes, that's right. That's more accurate. Now, can you superimpose the? Can we? This is phi, right? Can you superimpose this d phi negative d phi d theta, which is a sine, right? Which is a sine. Be careful. You have to draw this one. You don't have to draw one stroke. You can stop in the center. Yeah. Sine, right here. It is sine. That's right. That's right. So this one will represent that negative phi. So question, what is d phi d theta?
Negative side.
No, it is epsilon. That is induced voltage. Can you see? This is the induced induction induced voltage. Okay, which is actually the Faraday's law. Can you see? So today we actually go to the detail of Faraday's law. And you can see once you can work out this first derivative, right? So we're starting from the phi, right? Once we work out this phi, then we can determine the induced voltage.
Yeah.
So that is how electricity generator works. So we have to thank Michael Faraday. Also, he made an enormous amount, very important contribution to chemistry as well, right? Michael Faraday. All right, shall we start? Any other questions?
No.
Okay. Yeah, we'll continue your mathematics next week, right? Okay.
Yeah.
I will save that. I will save that one. I will send that to you. Okay. Goodbye.
Bye. I'll see you next week.
Okay.
Thank you.
You're welcome.